Well, hello and welcome to another installment of Linear Algebra. Today we're going to continue our adventure into talking about determinants. And just to give you an idea, we haven't really talked about finding out what a determinant is, but we're going to sort of work our way through some of the properties we want it to have. And then sort of at the very end of this unit, we'll talk about how to calculate a determinant, and then hopefully sort of like its use will sort of become immediately apparent. Just as a quick sort of like recap of what we did yesterday, we figured out some basic properties of the determinant, and we're going to use those today to prove some important facts and to look at some determinants of some very basic matrices. And so the first thing I want to open with is it's a new proposition. Well, let's talk about what those fun facts are. They're here. Remember, if my matrix A has a column that's 0, the determinant of the whole matrix is 0. If it has two columns that are equal, the determinant of the whole matrix is 0. If one of the columns is a scalar multiple of another one of the columns, the determinant of the whole matrix is 0. And if I have any two columns that are linearly dependent, then the determinant is 0. This is actually really useful, and we talked about it, but this is how we're going to sort of leverage something about the determinant to tell us about invertibility, right? So what we know, what we can sort of surmise from property D is that if you have a matrix that is not invertible, it will have a 0 determinant. All right, so we're going to start with a proposition, and we're going to call this one proposition 3.2, mostly because it comes right after proposition 3.1 proposition. And this is actually a big one, and we're going to leverage this later today even. So we're going to talk about some things that we can do to a matrix that does not change its determinant. And so this is going to be a little bit of writing, but what I'm going to say is the determinant of a matrix does not change if we add to a column a linear combination of the other columns. And when we do it, we leave the other ones intact, other columns intact. We're just going to mess with and we'll see what this means in a second. And so we're going to leave the other columns intact, and sort of like the particular reasoning is we can do this thing in particular. The determinant is preserved under what I'm going to call a column elimination. Operations. And this is a big one, and we'll prove it in just a second, and we'll talk about what that means. So, when you do the elimination method with a system of equations, right, you have maybe 3x plus 4 and 4y equals 12, and then you've got 2x minus 4y equals 6. You can eliminate the y's, right? You're sort of adding to one of the rows a linear combination of another row, and you don't change anything about the system. That's sort of the analogous thing that we're going to do, except for we can do that with columns in our matrix. And when we do that operation, when we try to eliminate entries in a column, we don't change the determinant. And let's take a look at why this works. We're going to see a proof of this. Okay, this is actually pretty neat. I like this proof. Okay, so we're going to fix a vector, and we'll call that thing vk. So fix a vector VK. And this is the one that we're going to like add to it some linear combination of other columns. So that one we'll call U. Let U be a linear combination of the other columns. Okay, and that basically means like U is like the sum of some index, and it's like all of the indices that are not K, right? I've built U out of some linear combination of all of these things, of like vectors and coefficients, but I don't have the vector K in it. That's really important. Okay, well then let's check the determinant. Okay, so and then we have the determinant of this matrix, and the matrix has got V1 in it, and then over here it's got like VK, but to VK we've added U, right? And then we got Vn all the way out here. So this is this sort of like elimination move that I've tried to do, and this is in the kth spot over here. Okay, well then, like, what I know is that the determinant is linearly linear with respect to columns. So by linearity, I can pull this out. I can say it's the determinant of like V1, and then I could just do the VK part, right? Because this is a sum, and so I can split this out. And then the other part that's left is the determinant of like V1, and then this is the sum I not equal to K. So everything that's not a K of like alpha K, VK, and then we've got Vn. And then, like, we've sort of seen a similar argument to here, but this sum has a bunch of vectors in it, right? And it's all of the vectors that are not in particular. Oop, these should be i's down here, I'm sorry. This is like an indexed sum of vectors, so we've got a bunch of them in here. And basically what this summation notation is telling me is that, like, this sum has got all kinds of vectors in it, but the one vector it does not have in it is K. And what you'll notice is also in this determinant are all of those other vectors. So V1 is here, and it's also in the sum. V2 is here, V2 is also in the sum, V3 is here, V3 is also in the sum. And what we know is that, like, if you have duplicate columns in a matrix, the determinant of that thing is 0. So when you split this out, the determinant of this thing is always going to be 0 because this sum is going to give me duplicate vectors all over the place. And so no matter how you try to rearrange this, this determinant is always going to be 0, which means the only part that stays is this one. So this is the non-zero part of the determinant, and that's the determinant that we started with. So what we said is if we took the kth spot and added some linear combination of the other columns, it's the exact same as if we hadn't done that. So we don't actually change the determinant when we do these sort of like column elimination moves. And that's our proof. And that's actually really important. That's one of the things that we're going to use moving forward to talk about some determinants of very simple matrices. And, well, that's where we're headed. So let's do this part then. Determinants of, we're going to call it diagonal and triangular matrices. So that's what we're going to do in this sort of like section right here, is we're going to look at how to compute the determinant of diagonal matrices and triangular matrices. So this is our sort of first foray into actually calculating determinants, as opposed to like talking about their properties or, you know, seeing what things we can tell about the determinant. Here we're going to make our first jump into sort of like figuring out, if we're presented with a matrix, what is the determinant? And well, the first one is diagonal matrices, and I will say a quick thing about a diagonal matrix. A diagonal matrices are all 0 entries except for elements on the main diagonal. And I realize we haven't really used this term before, but we'll talk about it in a second. Diagonal. The main diagonal, just as an aside, runs from the top left corner to bottom right. So a diagonal matrix, well, it looks like this. We've got maybe like we'll call this A1, A2, and then down here we've got AN. So this is that diagonal that we're talking about. These are all square matrices, and it runs from the top left to the bottom right. And then like everything else is zeros. The identity matrix is a diagonal matrix with all entries equal to 1. Okay, and what we want to look at is like, well, what is the determinant of this thing? That's what we're looking for. So we're sort of like looking for the determinant, and the way that we had written it before is we have this, we've slapped together a bunch of matrices. So we've got A1 and then a bunch of zeros as the first vector, and then like the next vector we've got A2 and a bunch of zeros, and then, well, we kind of get the pattern, got a bunch more, and then all the way down here we've got a bunch of zeros, and then AN. And we're trying to figure out the determinant of the matrix that has all of these vectors sort of slapped together. And what we're going to use now is this idea of linearity, right? So what I can do is I can pull a constant out of each of these vectors, and what I'm left with is like the diagonal. This is A1 times sort of like your E1 vector, or a vector that's 1 in the first argument and the zeros. And then I've got A2, and that's times this vector. And then we get a bunch more. I'm not adding. I don't know why I have pluses in there. And then I've got a bunch more. And then out here I've got AN, and it's all zeros. And then a 1 at the bottom. And then by linearity again, I can pull each of these constants out to the front. So I have A1, I've pulled that out, and then A2, I've pulled that out. And I'm multiplying them all together times the determinant. And what you'll notice is the matrix that's left when we slap all of these base vectors together is actually the identity matrix. And what we know about the identity matrix is that its determinant is 1. That was our normalization principle. So A1, A2, AN is the determinant of this matrix, which we'll maybe call it A. And so the determinant of a diagonal matrix ends up being just the product of all of the diagonal elements. And that's sort of our take home here, is the determinant of a diagonal matrix is the product of the diagonal elements. And what's really interesting to note, and what I want you to think about, is like, well, what if I have a diagonal matrix and one of the diagonal elements is 0? That'll tell you something very specific about that determinant, right? Because you will zero out the whole product, and we can actually think about that in a different way, because if you have a diagonal matrix where one of the diagonal elements is 0, say it happens like right here, then you'll have a 0 column. The 0 column is right here if it's got a 0 diagonal element, and we know from one of our properties before that if you have a 0 column in your matrix, that's automatically going to have a 0 determinant. So that sort of checks out in its own way. And the last sort of simple matrix that we're going to compute determinants for is a triangular matrix, or sort of in general triangular matrices. And we'll talk about what they are first. Triangular matrices. There's two types of triangular matrices. There's an upper triangular matrix. Upper triangular matrix has like diagonal entries A1, A2, AN. It's 0 below the diagonal. Then like above the diagonal, you've got a bunch of stuff. That's not necessarily 0. So star is just like general stuff. You got a bunch of entries. Maybe they're 0, maybe they're not. But everything below the diagonal is 0. That's what we're going to call an upper triangular matrix. That's a triangle that I drew. So as an adjective, it's an upper triangular matrix. And like, well, at this point, I bet you could guess what a lower triangular matrix is. It's got diagonal entries, A1, A2, all the way out to AN. Above the diagonal is all 0. And then sort of below it, we've also got the same, like, I don't know, junk. That's not necessarily 0. And this is what we'll call a lower triangular matrix. And what I'm going to contend, my contention, is that a triangular matrix like has a determinant that's the product of diagonal entries. So we'll say like det T equals A1, A2, AN if T is triangular. That's what the T stands for. Wonderful. Well, how does that work? Well, I want us to think of sort of like a fairly simple example. We'll use an upper triangular one, and the case is sort of general, so you could do a lower triangular one if you wanted. But we'll start out, and I've got a triangular matrix, and it's got A1, A2, a bunch of stuff. Actually, I want to do a couple more of these so we can illustrate A3, A4. And it's got as many entries as you really want in it. And then it just has stuff up here in the top. It's all zeros down here, but maybe it's got like an element up here, and then maybe it's got like some other elements here, which I'm going to do as like triangles, and then maybe it's got like some elements here. You'll notice A4 has 3 elements above it, and then A3 has 2 elements above it, and A2 has 1 element above it, and then A1 is like it's a diagonal entry. And the key to understanding why the determinant of a triangular matrix is the same as the determinant of like a diagonal matrix, it's the product of all its entries, is we can do these sort of column elimination steps to T to make it diagonal, right? I could like, and what's important to note is that these column operations, or the column eliminations, preserves the determinant, right? So when I do these column operations, I don't actually change the determinant. So I can change this whole matrix into like a diagonal matrix, and that determinant will be the same as the one that I started with because all I did were these column elimination steps. And what that sort of looks like is like the first one I would use like A1 to eliminate star, right? I could use like, you know, if star was like 2 times A1, I could take the second column and add 2 times A1 to it, and that would get rid of star. That would make that a 0. And then the second step I would use like A1 and A2 to eliminate the triangles, right? I would eliminate these 2 terms using some linear combination of like A2 and A1. And we sort of get the pattern now. You could use like A1, A2, A3 to eliminate, like you get rid of all the pound signs, and then you could do this all the way down until you would like end at a diagonal matrix. And we know that the diagonal matrix is like, well, the the determinant of this diagonal matrix, the determinant of like D is a diagonal matrix, is the same as the determinant of the triangular matrix I started with, because the only thing I did were these column elimination steps, and the column elimination steps don't change the determinant. Okay, well, that was a good little stretch. We're going to take a break, a short break, and then we'll come back in a minute.